This is about a part of the study that gave rise to this paper, which came out about 2 months ago in the JGP. And these are, this is our AI approach. These are the authors. There is one author missing here that I will talk about later. And as written here, this part has nothing to do with the AI part of the study. It's all in the post-processing stage that all these AI approaches need. And so it's a limited ambition journal club, but for that reason, I had to make a few clarifications. I have to beat our drum a little bit, but before I do that, all this part is something that was essentially forced on us by the 4 referees that work on this submission. They made us do it. But after the effort, it turned out good because the addition was important. The author that I'm going to tell you about later, Lucas, realized that it was important to the level that it required a change in title, which was this introducing, at his suggestion, the term volumetric here, because it really allowed us to go from the image, which is a two-dimensional entity, to volume and concentration of chemicals in those images or in the tissue represented, to the point that the authors went for a highly critical to a highly appreciative position, and you got an editorial commentary from Joachim Nielsen, who works in southern Denmark, noting in the title that the technique allows the field to move beyond homogenates. In other words, instead of chopping everything and putting inside the blender, we were now able to get something like concentrations in different regions of the cell at a high resolution level of EM. So Nielsen got carried away and he put in X, Twitter, this year, it is 20 years ago that I and Niels Ortenblad started to quantify glycogen granules manually. And now Eduardo and colleagues show how AI can be used. So this got retweeted. I think now you have to call it re-exit. Like 30 times. So it was the closest to viral that we've ever. Anyway, okay, so is what?
There were probably some bots involved that helped them.
Right. So we start with just the brief recall of this AI business, which I've talked here twice already. This is one of classic images by Montserrat, and Montserrat is in the audience. So showing a skeletal muscle cell stained for glycosyls. Yes?
Yeah.
Okay. Stained for glycosyl. Okay, so this is the mother image, of which we have many for human muscle, stained for glycosyls, glycogen granules, 30 nanometer in diameter. And so this is what our AI models do, or one finds for every pixel, where is the pixel located? That's why they call that segments. So the image is segmented, therefore semantic segmenter. And this is another segmenter. It segments according to whether the pixel is in the granule or out of the granule. And from the ratio, combining the two, we get the ratio of pixels in granules over pixels in the location, which we call PF. That's a number between 0 and 1. And that's what all the AI models give us. From there, we want to go to VF, which is the voxel fraction. And what I wanted to make sure people realize is that pixel fraction is entirely analogous to the same as area fraction, and voxel fraction is volume fraction, fraction in the volume of glycogen granule. So volume fraction is what we want, because from there we go to concentration of glycogen in every region. And that's what was valued by the reviewers. So here I'm presenting an ideal situation where the slices would be exactly the same depth as the diameter of the granule, 30 nanometer, because in that case, I could demonstrate it in different ways, but I think it's intuitive that VF is roughly proportional to PF. Is what?
Average. The granule diameter is same. It's average.
Right. It could be, it's same idea more or less, but you're right that the diameters are shown in this rendition. They are also shown the same, and they are not. That's a little complication, but in any case, this would be an ideal situation. It's not a realistic situation for several reasons. As you said, diameters are variable, and also this is not the diameter of the depth of our slices. So it's more like this. I was playing with morphing. But this is more, it's a better representation, still with diameters all equal. We still haven't introduced that complication, but this is a better representation of reality. And this is even better. Now, look, seen from the side, or maybe it's not like that. Maybe it's like that. Maybe the cutting blade shaves the granules smoothly. And I checked that with Clara, and I think Montserrat will agree that this is the case, that the blades cut the granules and you are left up with something like this. This is getting more realistic. So now you may be wondering what's this Cheshire Cat smile and how is Eduardo getting so sophisticated in renditions. So
the when you look at the binary which you showed,
yes,
there seems to be a big variability in diameters. Is that because of the cutting?
among other things, it's real and it's because of the cutting. The granules are all distributed in size. There is a distribution of granules. And there is also the problem of the cutting. And the problem of the cutting.
It's quite a big variability in diameters.
Of course.
But is it because of granules?
It's both. It's both. You cut and you eliminate the bigger part for it. Or you have a small granule.
From what you know about your data, is it primarily the cutting that gives that impression, or is it variability, true variability in size?
The very small ones are because of the cutting. The granules are definitely that we see that we can identify a granule. Maybe it's our own limitation, 14 to 40 or 45. That's the range of real granule that we think we can see. Yeah. But then the cutting makes it complicated. So I don't have a very full answer for what you're asking. So anyway, I was telling about this guy. This is Lucas. And Lucas, in addition to making all this, had some important influence. So I'll tell you a little bit about Lucas. Lucas, since he came out of architecture school in Montevideo, started to making a name for himself in Uruguay, back in Montevideo, doing what they call recycling. So this old classic home, family home, was converted to a bookshop, recycled as a bookstore, and was considered the recycle of the year, was given that award, and he made big changes. He's a very audacious kind of guy. For instance, side, he only left the sunroof of the old house. And then he came to Santa Monica, California, and since he got there, he started making a name for himself. He built the thing in 2002 and was considered the building of the year by some, I think it was the city of Santa Monica itself, right? So that's it. And so like 10 years ago, Lucas, who's a good friend and also my nephew, sent me a magazine of the American Physics Society. And the magazine had a fantastic article about AI, giving the basis of AI, and got me hooked. And that was the origin of all this. And then here, it had a lot of influence too. So I sent him this problem and asked him to start using his resources. And he was the one who started making this drawing that or rendering that helped us think. Okay, so back to the problem, and with another of the Lucas things, I asked him to put a plane in the middle so we can think of the actual Montserrat slice as the sum of two half slices, which are ideal, as I said. In those half slices, we can think that PF and VF are proportional, which is roughly true. So now we can rethink. Okay, so here is the two-dimensional binary result of AI. This is what we get. Yes.
Can you mute yourself?
This is ideally what we would like to have, but we don't have. Follow me because this is the only math. What's coming is the only math in the whole talk. Okay, so here is PF. That's what we know. We would like to know PF1. And we would like to know PF2. So, but those are unknowns. We want to play with them. We're going to call them X because we don't have any reason to believe that one is different from the other. So we're going to make up PF from these two X's. If we were in a very diluted condition with very few granules, it would just be the addition, right? They would just be additive. So PF would be PF1 plus PF2 or X plus X. However, as we get higher in concentration, we start to have a problem of overlap. So we have two granules that are counted as one. We're getting down, we're making an error of minus. And what's the error of minus? Each one of these x's is a probability, actually, between 0 and 1. So the probability of overlap is x squared.
Why is it X plus X? Because they're basically the same granules and just...
No, they are not the same granules. When they are diluted, you have two independent half slices, which are, they just add.
But if you're cutting one in half, you double count.
No.
One big, one small.
No. There are two. I'm imagining that they are independent. We'll get back to that later. But if they are independent,
Whole slice, cut it
yeah, you
in
cut
half.
in.
And if there's a thing sitting right in the middle, exactly where it's supposed to be, perfectly centered, it's the big slice.
Right. That would be part of the errors already in our previous slide where we said PF and VF are approximately proportional if the slice is 30 nanometer. Now we are forcing two slices to be 30 nanometer. So for each one, we calculate X, or we call it X, we calculate the PF, we call it X, and we make the PF of the full slice as the sum of the two. No, it worked. However, that works if they are very diluted, because then if they are not diluted, you start to have granules on top and granules on the bottom that overlap, and they are counted only once. So
essentially assuming no cutting. You're assuming...
Yeah, you're assuming...
physically in the
Yeah, you're assuming that that's a small granule or something. You're too smart. You're getting into my nerves because you're getting into my last slide.
So why do you assume same X for the two slices?
Because you don't know nothing about them. You cannot think what you think of one, you have to think of the other. They are equivalent. So as unknown, you don't know what they are. It's the same unknown. No, they should be approximately. It's random.
So if it's just solution and some kind of
So I'm going for the average X. I'm not going for the individual X. I'm going for the average X. That's what I'm interested in. These things have a lot of variability for sure. They are not going to be equal, but their average is going to be equal if you want. That's a good point. You know, if you average the one on the top and you average the one on the bottom, you're going to get the same because you don't know whether the one on the top and the bottom are different. Guys, this seems so.
Keep going. Get going. Let's see what's going to happen.
Okay, so well, anyway, from here, this is very simple, right? Because you just move things around and you get the equation of the polynomial of the second degree equated to 0, and that's the solution for X. Okay? Well, that's my solution for X, and that's what I wanted. This one I can go directly into volume. Because this is a PF of a single slice of 30 nanometer. Believe me. Okay, so this is it. So this would be X if it was not corrected. This is the X calculated with this formula. So it corrects upward. It corrects the error in minor. The more concentration you have, the more you need the correction because the more overlap there is. So this would be our theoretical corrected half PF. This will be in half the slice, right? So from here, we could go to volume, and you see that in the PF values that we find in real life in Montserrat images, they go only up to 0.4. The density or fraction in real life only goes to 0.4. So this correction is minor, maybe 10% at most. All these things.
X over 2. Okay, got it.
Right.
Okay,
PF over 2.
got it.
Half. Right?
Okay.
Because it's a half slice. But it turns out that it's not like that, right? So, but here for us, in our reality, it's a minor correction. So all these doubts that you had are and that I had are minor, really. But from this we derive VF, we derive the concentration on glycogen, and I wasn't happy. I wasn't happy because of what you said, because of the problem of the caps. I call it the caps problem, the problem of granules being cut. And that, as you can see here, all these three have the same silhouette. When the AI gets to this slice, it's going to give us the same value, the same contribution to PF of this one, and this one. They have the same diameter. And it's wrong. And it can be very wrong. We thought it could be a big error. There is another error, which has more to do with your question, but that will come later. So that's where, yes.
The other slide where you have the correction and the function, this one here. If I remember the very first picture you showed, the original EM picture, these granules were far evenly distributed. they were accumulating at certain locations. So
Mm.
where does this function now applies to? Yeah.
So this for us here, this will be random, approximately. Here not, but that's another issue.
Right. And if you look
In all these places, we model them as random, randomly distributed, random sizes, everything.
So you're cutting this image into a bunch of smaller images?
I am.
Or is that a statement or a question?
uh,
Okay. In that big image you just showed, you showed one red box.
mm,
Are you cutting that big image into a bunch of smaller boxes?
No,
Or are
no.
you taking the whole?
No,
image?
I'm taking 1/4 of that. I'm dividing. That was too big to handle, so we divided. No.
Okay, so you have a lot of inhomogeneity.
Uh, in the region here, this is exactly 1/4 of what you saw, half and half.
But if you're ending up with concentrations,
Yeah.
what's the volume that you're referring to if you think about it in terms of a cell?
That's the volume of the SR or the volume of the intermyofibrillar cytosol or the volume of the A band or the volume of the I band.
So it's not
No, because
not
it's by
including the sites.
it's you can add everything together, and then you are supposed to get the homogeneous get. Or you can separate. That's the beauty of this is that you can go region by region, and over hundreds of images or thousands of images, the AI produces the PF for all the SR or for all the intermyofibrillar rapidly in seconds. So this number can get very precise and for every region.
We didn't go into that. Maybe you can say one or two sentences to that. To generate this semantic segmentation
Mm.
determines the different regions of the cytosol. Or
This
the
one.
cell.
This one.
Yeah. The A band, the I band.
Yeah.
Yes. What feeds into the segmented to make the correct decisions?
The training, because you give them images like that, segmented by Carlo or by me, by Ishwar. We were working on that for a long time. Segmenting ourselves to get a bunch, and I'll get back to that soon for an important reason, but we had to work a lot on hundreds of images to and then we decide, right, we decide. And then we give it to the little brain, and the little brain gets trained. And then they can do rapidly many thousands.
Then you probably took another set of data that you had
Right.
figured that had a test.
Yeah,
spit out the answers
you need to have the training and then the testing to make sure that
Right.
this little brain is doing it right.
But the training material for the algorithm
It's user defined. Right. That will come back.
Because you have to make sure that training data is correct. Otherwise
Right. Garbage, the old garbage in, garbage out. Okay, so anyway, one more. Okay, so we decided that we didn't like that solution, that you didn't like, we didn't like, and we decided to go full simulation, full numerical. So this beautiful thing made by Lucas summarizes the approach totally. We make baskets. We call these big things baskets. They're pieces of virtual volume where we put granules, realistic granule now, with the correct distribution of diameters, and then we slice them. And then we make our 60 nanometer slices, realistic slices, And then in there, because all these are data in a computer, we calculate the projection, which gives us the PF, and we know exactly the VF. With that, we know, because we know how many granules we put and how big they were. Okay, so we do that, and here is a problem. The first problem is how to make a realistic distribution of diameter, what you were asking. So we remember the time that our group worked a lot on calcium sparks, and we worked with Lothar and everybody on calcium sparks, that we had devised very good programs that had nothing to do with AI. They were just computer programs to detect calcium sparks. And we said, well, maybe we can adapt them. Again?
I know the chemical upside back. Good question. Let me go one slide back for your yeah, here at the bottom, you already have result of that box
Of this one.
black and white. So
Yeah.
this is the result
Of this one.
of this one.
Right.
Right? So by this result, you said you know how many granules are inputted.
Yeah, we know how many.
This is the right result, or this is the something.
We know how many voxels we have here. We put them there. So we know exactly how many voxels.
Okay, let's see the.
So we know PF because we calculate PF is just a fraction here, and we know VF. We know everything. So now, but it depends on how good the simulation, how realistic the simulation is, and that's what I'm going to talk a little bit now.
I have another question.
Oh, Montserrat.
Respect to the previous slide, aren't some granules very too tiny? Like this, yeah, some of them look very small.
I'll show you that in a second. Now you will see all what we did and how we did it like that. Okay? It's coming in a couple of slides.
Eduardo, in that previous slide, don't worry about it. You had the stack of simulated.
Hmm?
Do you have that same kind of stack for the experimental, for the images?
Well, that's what Montserrat does. He just cuts.
So the answer is yes.
Yes.
Okay. So why can't you?
Oh no, but she doesn't know no, that's too difficult because it's too difficult to. Huh?
You don't have a Z stack.
You don't have a Z stack.
Okay.
No. No. It's complicated. But the answer is effectively no. So anyway, going back, this is an original image or a quarter of an image, and I tried to make the spark detector adapted to find it. It doesn't even come close for the simple reason that the spark detector was done for fluorescent, and for fluorescent you had essentially the sparks are bright events on a dark background, very homogeneous, and it's an easy detection. Here, those programs didn't even start to work. However, as we were saying, the user had to train the little brain. So the users had laboriously gone over images like these and marked where, we thought that the pixels in granules were. So we had tons of images like this one. I think 94 images like this one. And with maybe 3,000 or 4,000 events or granules total. So we modified the spark detector to detect here these sparks, right? And that was very easy for the detector. So the detector found the sparks or granules in this case, and not only that, by contour them. And we contour them, which is a simple technique of image analysis, because we had to calculate the diameter of each. So now we're talking real stuff. And we are just trying to determine the diameter of all the granules that we label based on these contours.
So the contours of the program, the SPARC program, was applied to the human.
To the human label masks, binary masks. So for the SPARC program, it was very easy. And how do you find the diameter? Is the longest distance between 2 points in the contour, right? So for every contour, the longest distance between 2 points is the diameter. That's trivial. And then this is what we got as a histogram of the 3,000 some granules that the program detected. That was our histogram. And the histogram is discrete with peaks like that. Clearly, the one that matters is this one, because these ones are just measured on fused granules, right? So that's what you get when you get two like this, you get something that is about double, 60 instead of 30. Is that okay?
But, okay, yeah, I
Right.
understand that, but it still doesn't really account for cutting, because you still don't know how it was cut.
Yeah, you don't know. You don't know.
And also your granules are basically all the same size.
Yeah.
In the same, if there was a true.
They are not the same. They are
0.75
not the same size. Look, this is the actual distribution we measured. They are not the same size, not at all. They are narrowly distributed, but they're not the same size. So
You said before you mentioned you had a range of 40 to 45.
in there
That distribution.
to 40. Here for maybe 10 or 13 to maybe 40. 45 because this doesn't go really to zero. These are the biggest ones. Maybe they are mistaken. I don't know. But this is empirical. This represents all we know about distribution of granules. And this is consistent with what people have said, except that it's more detailed and people hadn't said that it was so skewed. There is skew in this distribution. It's not a perfect Gaussian.
But
But we didn't, so we now have to simulate this. And I'm getting near the end of the presentation. We have to simulate this. How? First of all, we have to simulate the diameters. And for that, we use a random number generator with a Gaussian distribution where you can set the midpoint and you can set the standard deviation, and we play with that. So we came out with two possibilities that more or less described it equally well. In one case, it was a normal distribution with mean 25 nanometer, which is this one we call small. And in the other case was a normal distribution 27.5 as mean. We made 3,000 of each. So this is a distribution of 3,000 simulated random numbers. And we used both. We couldn't decide on either one. So we decided to use both. So you are going to see really two simulations in parallel. We couldn't. They were, both of them more or less describe the phenomenon. So we're going to do the full simulation. And here is a summary of the full simulation. As I said, we made these baskets, which were half cubes. We didn't make the full cube, we made half cubes of 1 micron by 1 micron by half a micron. So if we put, as in this case, 3,000 granules, these are simulated granules, in this basket, we are simulating a concentration of 6,000 granules per cubic micron. And 6,000 granules per cubic micron is about the maximum of the range that we observed in Montserrat's images, okay, by our preliminary calculation. So from here, you can cut slices of 60 nanometers. We can cut 7 slices because we avoided the top and the bottom. And here is one slice. This is slice 0 of this basket with a very high concentration. And this is the projection. Okay, so we have everything, right? As I said, this full simulation solves the problems of the caps, right? Because we are doing exactly everything, reproducing in the simulation what the actual
So why you divide it by the six? The six, I mean 8 or 6 or whatever that was.
previous.
This one. So
Oh,
the
because
six-
that's how, because each one has to have 60 nanometer.
60
So you can put 7, not 6, but 7, 0
or
to
30.
6.
That's
Okay,
six.
that's the nerdy way of counting.
Right.
But by calculating that area, you're biased to smaller size because you're accounting for cuts, like, these gaps, and that's error goes there. Because you're thinking that it's small granule, but it's just, cut.
But it
over
doesn't
on the
matter.
top.
But it doesn't matter because it's real. It's real. You know how many. You are not assuming anything here.
But
It's
you
all
are
numerical.
assuming granules that size, but maybe there's no such granules at all.
Oh, that issue that we don't have a good. Yeah, there is an answer for that, but it's true. It's an inherent error of this paper, of this study. But you're right. But we said why that wouldn't be very important, and it will come up later. And I'm 20 of 20. I'm near the end. Bear with me a little bit. Okay, so the problem of the concentrations also is taken care because we cover the range of concentration. We made basket with 800 granules, 400 granules, 1200 granules, 16, like one. In other words, we went through the whole range of concentrations that we found. This simulation is good for every case. And this is the result. So here is a primary result. I told you we did 2 simulations. This is with the big granules. This is with the smaller granules. The big granules are centered at 27.5 nanometer. The smaller ones at 25. So here we are simply counting the granules per cubic micron as a function of the pixel fraction. So the granule per cubic micron, we know exactly. We don't need to count them. We know exactly how many we put. For instance, here we put 400 in the basket, 800, 1600, 800 in the basket, 1600 per cubic micron. And no surprise, for the same pixel fraction, we needed more granules to get to the same pixel fraction, or the more small granules. The triangles are the small granules. This is not what we are after. What we're really after is the volume fraction, which we know. Okay, so for every pixel fraction, we could compute the volume fraction. In this case, triangles are slightly below circles. The same pixel fraction require, the same number of granules require a little bit less, a little bit less volume fraction. The same pixel fraction got a little bit less volume fraction. But that's not the point. The point is that the difference is very, very small between these 2 simulations of very different sizes. In other words, the diameter doesn't matter. The assumption of the diameter almost doesn't matter. So that's an answer to what's been bothering Gideon, what Gideon says is true. We don't really know the real distribution of granules because we don't know if what we measure is caps or full granule. So you're right. But the point that this result makes is that it probably doesn't matter all that much. Probably the error is small. Okay, so what do we do with this?
In other words, you say the concentration, to measure concentration, it doesn't matter the diameter of the.
I didn't say that. I said that our simulation does it very well, even if we made some errors in confusing granules with small cut cups. And this is the demonstration that we have fully shifted distributions and we get almost the same result. Because we need to get a working formula from here to interpret our result. We are going to interpret now our result in terms of concentration. So we need a formula, and we decided to fit a second order polynomial to all these points. These points here are the same as here, right? We didn't distinguish. These are the small granules, these are the big granules, but we fit the whole thing together, and we got that. We got a formula for VF, simple formula coming from PF. So it's not proportional. As we know, we didn't expect it to be. It's a second order error here. It's curved upward very little. So now for some results, finally. These are 7 patients, images from 7 patients. These 4 in the blue boxes are MHS, susceptible to malignant hyperthermia. These ones in gray boxes are MHN, negative for the test of malignant hyperthermia. There is a difference. MHN have more granules. These are granules, volume fraction, have more volume fraction, more glycogen than the MHS. But the significance is okay. It's not the greatest, mainly because this one here is normal, but almost has no granules. But every one of these patients has different clinical picture. Malignant hyperthermia susceptibility is not even a disease, it's a susceptibility. So the people who have that may be completely normal or may have clinical problems. So Carolina devised a clinical index. So here are the same patients, the same images, the same values of VF, but grouped by clinical index. So 2 patients had a very high clinical index, 6.67. It goes between 0 and 10. And they had very low VF. The P of no correlation is now negligible. There's a very clear correlation between the content of glycogen in granules and the clinical index. So that was probably the most interesting result, take-home message from all this.
Experiment blind, without knowing what one was. Like,
Well,
you know the blinded, yeah.
this is not blinded. There is no way.
No, you know the result. Okay, this is from this patient, this is from this patient, and then the granules showing the same, but you try to go.
The clinical index was made before. So we knew she and Sheila Riasi had already figured out the clinical index before. We used this patient because we had a lot of images from them. That's the only reason. And that's why we have more disease than normal. And we were only 7.
You already know that this tissue has a problem. That's what I'm saying. If we taking the tissue, we have more problem, and this is not. I'm saying if you take a blind, 2 tissues, which is you don't know what's happening, you're checking, are you getting the same result or not? So that's the, I mean, again,
Was the person quantifying the images blinded to the samples?
yeah,
That's what you're
and then try
In a way,
The AI is one.
the AI doesn't know anything about it. The AI has no bias. The AI does the same for all of them. And then we apply the formula. So we have a AI that doesn't know what it's doing.
There's no human in the loop.
There is no, there is no adjustable parameters.
no, but after that you put it to the,
And then the AI give us PF. So PF
Yeah,
is
you find- yeah.
incorruptible, right? And then
Gives the oldest circle.
we apply this formula and get BF, right? So there is no way you can bias these. All these circles are different images from this patient, exactly. And we get BF for each one. So this is
in a susceptible patient, does the index have to be 0?
this patient is atypical.
There are 7 patients in this study,
Yeah.
right? Each gets an index number.
Yeah.
Right. For someone to be susceptible, as is that, if we have an index of 1,
that's good or bad.
that's sufficient to fall into the disease group or not? In the susceptible group, sorry.
For instance, this patient, I remember that he has an intermediate clinical index, even though he was normal. Right. Right, you are blinded to the diagnosis. That's blinded because they do it even before they get a diagnosis. They know the clinical index is made of family history, pains, aches, anything. And right, so for instance, this one had an intermediate index. This one had a very high index, and some other here maybe too.
So then the question arises, that's a different topic, but how well does the index correlate
With the diagnosis.
susceptibility to?
Yeah, it correlates okay, but it doesn't mean that there are no, this is it's a very small sample. So you can get outliers there, you can get anything.
I mean, you can be susceptible with a low clinical index.
Okay, you have examples like that.
Yeah, you can.
So this is the last one, which is kind of a summary, because here we are putting again the PF in the full slice. This is the simulation, by the way. It's not the actual. We're going back to the full simulation. So this is in the baskets, what we put. This is the PF in the full slice. This is the PF in the half slice, corrected according to the theoretical model, to the x plus x minus x squared. And this is the correction done by the simulation, by the full simulation. So you can see that there is a very big difference between the two. This one was very bad, consistent with the fact that you hated it for different reasons. It goes in the right direction. That's the only good thing that can be said about it.
Blue is on the slide or blue is about?
The blue is incorrect. The blue is how many granules you put in the basket.
Oh, the bus.
Yeah, this is the basket.
Yeah, yeah.
This is
Bus,
corrected.
the bus.
Yeah, this is what you get for volume if they were proportional. In other words, this is proportionality. This is the correction with the x squared deal. And this is the truth, let's say. And you can say that the correction is, the only good thing about it is that it's progressive and and in the right direction, but it's completely wrong. And probably you have figured out already what's the worst part of it. What was the worst part of the assumption? But if you don't, we can finish here.
Really cool.
Huh?
Really cool. I have a question, but I want to preface my big question with a smaller question. What do you get out of the Montserrat data? I know you get, I see each image. How many images, and since you don't have a Z-stack, what are they? Like, you get one image per cell? How many images per cell do you get?
Maybe percent.
Like thousands, hundreds, 10, 1?
No, no, you
Just slicing, yeah.
you don't know. You don't know.
You get a lot of slices.
You get a lot of slices, but you don't get them ordered.
So now, okay, good. So now this sets up my big question.
Right.
I'm really intrigued by your simulation data. You have a box, you can put all these things in. So you actually have perfect data. And you could generate, in principle, all the training data that you want for, like, you have all these things here, you could make granules here.
You cannot
like,
generate
no,
training data. Oh, you are assuming that you can.
No, you have your simulated data here, right?
Mhm.
You do that. You do a whole bunch of those, thousands and thousands of different kinds, and then you know what the distribution is of the sizes because they're inputs. You know what the PF, the VF is, and everything. If you did like a simulated Montserrat experiment based on that same volume, you get all sorts of cuts in different scattered random order. You get all the same images, but in random order. You don't have a Z-stack. Can't you make like a big AI program?
No, you know why
that will
not?
take all those simulated images.
You know why not? Because all the simulation was done on the basis of human interpretation of images. You cannot simulate Montserrat experiment because of the background. You cannot simulate the background. The background is completely variable, and that's the big thing that AI does. How do you simulate the background?
What do you mean by
No,
that?
but the AI finds your circle, right?
AI doesn't find. Okay, so how do you simulate the background?
I don't care about the background.
Well, so this was done by a human.
I'm talking just about the grant. So if you go to one of your, go back one slide. Okay, that one on 13.
This one?
13. That's a real slide, right?
No, that's a simulation.
Okay. But you have your segmenter find all your granules for you.
Mm-hmm.
So it makes a slice like that of an image like this of that what it thinks are granules.
Yeah, this is the output. This will be the output of the AI.
Yeah. Okay. So can't you sort of make simulated experiments from a box of spheres?
Isn't that what we did?
But you could then have the AI get back for you the distribution of sizes because that's what you put in. And you could get back for you all the other stuff that you want to know about your
It's exact. You get exactly what you put. You can do that too. In other words,
then you apply it to your actual image.
okay. So here you can do two things. You can do this, which is what you do with the real And you can calculate VF by AI. You can feed this and calculate VF by formula. What else could you do?
What I'm saying is what you're actually interested in is not just VF. You're interested in a lot more data. For
Right.
example, what is the distribution of sizes? And so you have a more bigger AI program that also gets you your distribution of sizes, because you can take your simulated data and you know the answer. So you can have a perfect training set, and you can have a really large training set for all the data you ever wanted to know about your granules.
But the problem is that you cannot train anybody with this. How can you train with it if you don't have background? I don't know. How? That's a problem. This thing is completely clean, but it has no training value because it doesn't have the difficulties of the.
Identify circles in your images.
Well, that's trivial.
Yeah, but you could simulate the background to see the sensitivity.
And you could simulate. Yeah. No, if you simulate the background, it's different.
But you've already found your circle in your experimental data.
In the experimental data, the AI hasn't found the AI finds the circle.
Exactly. But you have that. You can take that as data input. You can say, this is my input from my experimental data, or this is my experimental data. Is this washed image?
Is your experimental data plus the AI?
Yeah.
And then what?
So then you have it's called 1,000 images per cell, whatever. So you have 1,000 of these images in a cell, and from a cell, and what you want to know is what is actually the distribution of sizes in that cell. From this data, you can't figure it out. But from your simulated data, you could give it a whole different bunch of ranges of spheres and train based on this ideal data. What would that distribution of sizes and whatever other information you want to know about your granules be if
how do you know in these 1,000 AI process real images what the real distribution of diameters is?
No.
They all have the same problem.
He means to make a simulated experiment where all the data is fake, and so you know all the answers.
Your training set is simulated data, like Bob said. Then the thing that you're actually trying to understand is that AI washed experimental data.
You train
But
on
since
it.
that AI washed experimental data is all spheres, you can simulate all the spheres, and you can make an AI based on training set that is just simulated, and then you simulate some more, and then you test how good that AI that you made was based on that. And if then that's good on the simulated data, you throw it against the actual AI washed experimental data.
And you can do eccentric spheres. You can do ellipses and have some excitement.
Yeah, you can do all sorts of complicated things. Yep.
Yeah, but what
you're
talking about is in fact stereology. There's a whole science of how to do that statistically. That's what Brenda did a very long time ago.
Brenda should be here.
Well, you could just type into Google nowadays. There are many books on
I know.
size analysis
I know.
by statistical sampling. Okay.
You can also just throw AI at the whole problem and not learning statistics.
But Dirk's idea of using a defined data set to do the training, I think, is brilliant. I think it's a brilliant idea.
want to hear you say it.
Eduardo,
Okay,
let me
anyway,
ask a much less sophisticated, completely naive question. Well, I know nothing about AI. So when you give it a training set, all right, what are you giving this to? Is there a program called multiple programs called AI?
No,
I mean,
no, this is something we made. This is something we put together. It's a computer program.
So what makes it
It's,
AI?
it, because it learns, because it has intelligence in that sense. It learns. It
How?
takes this.
How?
It takes how.
Yeah,
Well, that was
it's
my
mathematical
that was my
procedure,
two.
so you can answer the question. How does it do it?
It does it by fitting a model with 20, in this one, 40 million free parameters. It's fitting a model using the variable, the input measure variable, so to speak, are the pixel intensities in every one of the hundreds of images that have megapixel size, right? So we are talking many hundreds of millions of values, which you give to a program that is capable of fitting a model, a mathematical model, implicit, never explicit in a formula, but it's a mathematical model, and it optimizes that model until it makes a very good fit. And it can tell you
How do you know
where
it
the
gives?
granules are.
How do you know it gives the right answer? But it's independent of the optimization method and so on.
Because you have a test group, then you have your testing images are divided in 3 subgroups. One is the training proper. It may be a couple of hundred images. The artificial network or model or little brain, like my wife calls it, uses that to learn. Then, every now and then, in the process of learning, you pass it through a validation group. That validation group, the model doesn't know, the artificial network doesn't know the right answer, but you can compare its answers with what you know, and you see how things are going. And when you get to a certain point in the validation, you stop and you say, probably I'm not going to get any better than this. And then you give it the third subgroup, which is called the testing group. And the testing group is like the final exam of some girl that was studying physics for a year, right? It's the final exam. The other ones are the semester test. In the final exam, the little brain doesn't know, but you know, the professor knows. And that's your final evaluation of your artificial intelligence device.
But of
which
course,
is
you
called
can get artifacts. There are lots of papers demonstrating that these procedures can give totally false answers.
Yeah, sure.
Okay, so it's not ordinary science. It certainly is not mathematics. In ordinary mathematics, the whole point is to be able to have some a priori error estimates.
Intuitively, what AI does is interpolate the data. So
Yeah, sure, but that's all
problem,
you need.
no, I'm just saying, same problems, the same pluses and minuses that you have for interpolation, the same wariness you have to have of interpolation you have to have of AI. So it can do a beautiful job interpolating data. It can do a wildly bad job interpolating data. Just like if you have a row of ducks that are perfectly aligned, and you ask for an interpolation of it. If you get the wrong interpolation, it will do this. It will go through all the points, but it will wildly sinusoidally off in the middle. And so if you have a model, it doesn't work. But so there are. I'm just agreeing with Bob. There are times when it can be wildly wrong, but there are other times when it can do a good job in fitting it, and that's the caveat.
Wouldn't that performance be obvious in the testing stage?
Eduardo, there's a substantial literature. Look in the SIAM, there are SIAM journals devoted to this. And there's a huge amount of work going on right now trying to find out how to minimize the artifacts and where they come from. This is a question that is attracting some of the best mathematicians in the world. But the crucial point about AI is it uses a very limited data processing in each step of the analysis, and then it does a very large number of those. That's what's different compared to what went on for a long time. But what is really nasty now is that most of the papers that do training simply don't tell you what the training is and don't give you any way to objectively evaluate it. Now, I'm not saying it's wrong. I'm saying that the people working in the field are not using the usual standards of numerical analysis. You can't publish a paper running on a new method of integration and not say what you're doing. And the training, the first question you have to ask,
let me say something. In a much lower scale of what we were interested in, we published the method, and it's really transparent. It's all in there. All the program. We understand everything we did.
Eduardo, there are lots of theorems proving that there are always counterexamples. I'm not an expert in the field. I just have looked in SIAM review, and there are articles that there actually are theorems proving that there have to be counterexamples. Okay, so the point is this area of mathematics, and what I'm trying to say is that people don't make up the rules in numerical analysis. When you do numerical analysis, you have to say what you're doing, and you have to say what are the artifacts and how other people get different results. And my problem with the training is I simply don't think that it's objective. There's the papers I've read don't tell you what would happen if you used a different training procedure, or if somebody's motivation was to get a different answer. And I'm sure that will work itself out. I'm not trying to be too negative. I think it's profoundly important, but the artifacts have to be addressed. I'm not talking about your method at all because I'm ignorant of it. So don't take this personally. I'm talking about the whole field. But this is the way things go.
But what do you want us to do about it?
I want you to read the literature of the math and cite it and understand what the theorems are. Just like you would for any other numerical procedure. You ask me, I'm telling you. I don't think you've read those papers. I don't think you know they exist. Now, if I'm wrong, you can tell me I'm being rude. That's perfectly okay. But there's a huge literature of this, and I don't think it's up to scientists to make up the mathematics. If the mathematics is useless and not helpful, fine, say so and get them to help you. But this is a very, very active area of research. It's extremely important. It is often the case that scientists discover things without really knowing why they're working that turn out to be tremendously important. I'm not denying any of that. But you need a flow from the empirical approach to the established approach. Back and forth. That's what I'm saying.
Yep.
And with present search engines, it's probably as simple a matter as going to the new ChatGPT, which is extremely good, and saying, what is the literature testing training methods? What ChatGPT, you need to ask it to find the literature, and it will probably find the key papers.
My last attempt, Bob, to try to get some common ground. In the last testing stage of training, one gives these devices, these programs, one gives them a labeled image, labeled by a user. An image, but the program doesn't know how the user labeled it. And You ask the program to label it, the program to label it. And then we compare, and we find a very good match between the two.
In the finite number of cases that you have studied, Eduardo. Listen, let me put it in very human terms. If you gave this to an aggressive graduate student and you said, can you find a counterexample? He could find one. That counterexample means an example where it looks as if it's satisfying the test and it isn't. It's like doing an integral. You can think you're getting the integrals. Let me finish.
No,
You do an integral
but it's
and
not an all or, the answer is not all or nothing. The answer is a fraction of pixels where it is consistent with what you think. And that fraction of pixels is of the order of 85, 90%.
I don't want to keep arguing about it, Eduardo. It's not an area of expertise of mine. My constructive work comment, which is entirely constructive, is that there is a huge literature on this. There are experts on it who would benefit enormously by working on your problem with you. Okay? But they have to be reached out to. It's completely constructive and it can easily be found. The literature can be found. And if I'm wrong, I still will have benefited you a great deal because these people are bright people. They are likely to give you some insight and you will give them very useful applications.
All right. Okay.
Great talk. I found
Okay.
it very, very stimulating.
Okay, Bob. Thanks.
All right.
Fred?
Oh, I see.
No.
Eduardo, I have a question.
Mm-hmm.
Can you hear me?
Yes.
One thing, like, I wonder if one would be able to get more information from the glycogen granules in the I band in order to determine the diameter, because there they are confined in 2 dimensions, so they can only run parallel up and down. So maybe if one could take how many there are and how much is the distance, and maybe that could give more insight on the dimensions, on a correct diameter.
I didn't understand how that would. What is exactly that you are asking? I missed
Oh,
it.
to take advantage that in the I band, the granules are already very confined.
Yes, they
Because
are aligned.
exactly. So like then maybe one could count with your program that you can count how many like the maximum distance, and then count how many there were in between. And then
Like,
yeah, like here, like here there would be 4 or 5.
they are touching. They are basically touching. They get as close as possible as they can get.
Exactly.
Right?
So that could be a way to get their diameter. Because they cannot,
But did I?
after they touch, they cannot get closer than that.
Because you mean that there is real, it's not a cap.
Correct.
Yeah.
Yes. So they have oriented for us, kind of.
Or at least by looking at the distribution of those, you can see what the cap might be, and you're using the imposed structure on the granule to gain more data. Although then you're assuming that the structure doesn't change, doesn't limit the size of the granule.
So, sorry that I'm meeting. The idea should be, I think everybody more or less got the idea that the problem that this method still has, in addition to what Bob may have added, is that we really still don't know the true distribution, because even in the actual this determination with the Spark program, we still didn't know if those things were caps or granules. So in the journal article, we have of course, we knew that problem, and we have a way out, which we indicated. It's very costly. It has to do with iteration, but maybe it's something with what you were.
Yeah,
It's a whole bunch of.
a different way out of that same
Yeah.
problem.
But we didn't do it because it would take a lot of work.
But that idea of looking at the
Okay.
IBAN,
Yeah.
I mean, I'm simplifying, but could that almost reduce the problem from a three-dimensional problem to a one-dimensional problem?
Like here. What do you mean in one dimension?
It's a 2D problem. It's a 2D problem. Or is it not a 2D problem? Did they line up in a plane?
Mm-hmm.
Like, did they line up in a plane like this, or is it just sort of in a string?
Who knows? This looks like really all granules of the same size, perfectly aligned, like in a collar, in a necklace.
Right. No, I assumed that it would go this way, but then I see your point that it might just be a string of granules instead of a plane of granules.
Yeah, I would swear for these diameters here. I think this you can take to the bank. These are not caps.
So if you use that as your,
Huh?
It's close to middle cut.
Yeah, it
Yeah.
looks.
so if you use that as your assumption for your distribution.
Oh no,
but
because
that's what Montserrat is saying.
but this is clear. Here, our program does not do well for other reason, which is we didn't assume this distribution in our boxes, in our basket.
Right,
You know?
but
So
that's
this
what
is
Montserrat
I
is
put this here because this is a demonstration that we still that we're still not entirely okay.
So I think what Montserrat is saying is that from these kinds of images, you can get a distribution.
Except that it's only the distribution of the granules that are in the I band. They probably have a physiological reason to be there, and probably are mature granules, ready to be consumed. Ice creams there that ready to be licked.
That's what Montserrat, I think, was suggesting, but there are
Yeah.
caveats to doing that.
Right.
Yes.
Right. It's a complicated problem. But the other thing is important is this, which I noticed here. It doesn't make a lot of difference. So we're probably worrying too much.
Yeah, but maybe,
Come on.
during your distribution, it's also, these peaks are pretty close, so you wouldn't really expect.
Yeah,
much
they're not
difference
wildly different
No.
distributions that you pick.
here. Yeah.
The true test would be to pick some.
Yeah. No, I should do it. I should. Yeah.
Now, to go back to that these data are from actual patients. You showed in one slide that the ones with the high index have low levels of glycogen, correct?
Right.
Do they have a different distribution of sizes?
Yeah, that would be good.
Because if they have less granules, you don't have the code to do what you went through. They just look at the images.
Well, the thing is that the images were from many different patients. We used whatever we got. So we got 94 images for training. And those, again, were randomly chosen. They had to be randomly chosen. So your suggestion is very good, but it would require designing for that. It could be done, sure.
Right, and
But
that's,
from
but
your data, can you say whether the
No.
group at 6.67, the granules on average are smaller or the same?
No, you're right. What we could do from the AI produced, because the AI produces two things, produces granule count
Yeah.
and volume.
The count,
And so we could divide the volume by the counts, and we will have your answer to your question. We haven't done it. It's a really good idea.
and that's why I also like, why I'm advocating for my approach of having a general approach that gets you distribution of sizes, so that you can answer more general questions. Whatever
Right.
else you want to know, actually. Also.
But this is very nice because we already have the data. And it didn't occur to us to use them that way. All right.
Thank you.
Okay, thank you very much.
Eduardo, before leaving, I have a short question. What if you in the patient data, were you able to see in different places, like in the A band or I band, if there are differences? Because my feeling is that in your graph you have everything together, right?
Or you will have to repeat slowly.
Yeah, that it looks like in your data you have like the sizes or the concentration of granules is in the full image, right? So the question is whether you could see differences in the I band with the A band or different places, like to see if there are, if that's some
we
sort
could do that. We could do that too. That's how that was Lothar's, similar to Lothar's question. We could go by region instead of going by patient.
Right.
Same idea.
Or patients, regions and patients, in a way to see if
patient and region.
Right.
I think this is what, because what happens is this was published as a methods paper in the JGP. And I think our lab probably published like 7 or 8 methods papers. This is the only one where somebody is now using it with our help. They already implemented it and they are using it. And I think they are using it precisely for things like you're saying. So finally, we got a method that somebody is using.
Good. Okay. No, but beautiful work.
Okay. Okay. All right.
Okay. Bye.
Bye-bye.
Okay. Thank you.